Okay, so can you hear me? Sí. Let's see if I can see the chat here. Okay, so you can hear me. Okay. So now we are going to talk about Lab 3, which is actually Lab 2. We are verifying the enumeration of the labs to be consistent with the web page. But you can download it right now. It's under Lab 3. Maybe in the afternoon it will be Lab 2, but the contents will not change or not change much. In the lab, you will see a list of exercises and also a notebook called wave equation, right? And the idea of the exercises is to see the wave equation notebook and do some things playing with it. Okay, so I wanted to go over the wave equation notebook just to clear any doubts and to help you understand it. Okay, and also clear out doubts about finite difference operators and how we work with them numerically. So this is the notebook. Could anyone download it and check it out? Not yet. Okay, but can you see it in web page? I hope that's the case. Anyways, so you can follow it in your computer and run as I talk, if you wish. Okay. So what we are going to use is the method of line, right? The finite difference approximations, where we have some scalar system of the way. For example, we have the Lab 3. This is the Lab 3, okay? And this is in particular a notebook called wave equation inside the Lab 3 that's only for you to use. It's not for much. You can play with it, but the homework is in the other file, okay? So we have some equation, the advection equation in this case with propagation speed equal to 1, where we have the time derivative of u equals the spatial derivative of u, okay? And what we are going to do is to approximate the derivative with some finite difference operator, right? So we have a spatial discretization of our solution, and in this case we changed u to v, and we have that v will be the spatial discretization. The time derivative of b will be equal to some operator multiplied by v. This operator will be the one that does the derivative, right? So essentially we are changing one linear operator with this derivative to some other linear operator which will be an approximation, right? And here we are only discretizing in space, not in time, right? Later on, when we want to integrate in time this equation, we can use the methods that we used for ordinary differential equations, right? We can use Runge-Kutta method, whatever is appropriate for our problem. Generally, in this notebook, we will use Runge-Kutta 4. So it's important to distinguish between the spatial discretization and the time discretization. In this case, we are only considering the spatial discretization. Later on, we will do some conversions analysis, and we are talking here on the conversions on the spatial discretization, not the time discretization. Okay. So in this case, we are taking a grid of n points, right? We are continuous in time, and we will solve problems which are periodic in X, just not to have any issues in the boundary. So imagine you have a solution and the solution repeats itself. So taking one last point in the grid is equal to going back and taking the first one. Okay, that's the idea of making it periodic. And what we want to solve is the wave equation, where we have, in this case, the second derivative over time of a function phi is equal to the second derivative in space of that function phi, right? And at first glance, it looks like we cannot solve this with these methods because we have second derivatives, but it happens the same thing that happened in ordinary differential equations, where we had a second time derivative, but we just simply expanded the systems to other variables where everything is a simple derivative. So in this case, we define two new variables, u equals the spatial derivative of phi, and v equals the time derivative of phi, right? And if we do this, we have that the time derivative of phi equals v, the time derivative of v equals the spatial derivative of u, and the time derivative of u equals the space derivative of v, right? So we just take derivatives, right? This last one here is just that the derivative is symmetric. So if you derive first with respect to time and then to space, it's the same as first deriving with respect to space and then to time. And now we have this system. And what we can do now is simply focus on v and u. Because if we can solve this part here, this little part here where we have v and u, then we also have phi. Phi can be obtained just by integrating the solution. So instead of solving for phi, we will solve for v and u. Is everybody clear up until this point on what's going on? Okay, so now we see this system where we have u and v, and we have the derivative of v is something of the derivative of u, and vice versa. And we realize that we can diagonalize the system and choose some new variables, which we will call u plus and u minus, right? U plus will be the sum of u and v, and u minus will be the difference between u and v. And if we plug this in these equations here, we have that u plus, the time derivative of u plus, equals the spatial derivative of u plus, and the time derivative of u minus equals minus the spatial derivative of u minus. So with these variables, these two variables are completely separated, right? U plus goes only with u plus and u minus goes only with u minus. And the solution, the exact solution of this equation, is the solution of an advection equation, where you have the solution, the initial solution, simply moves to the left or to the right. Okay. So we have our original phi, and we can think the phi can be made by combining two solutions, one solution that goes to the left and one solution that goes to the right continuously. This is what will happen in the wave equation. So for example, if phi is something that does a bump, goes up and down, then we will have suddenly two bumps that are going away. Okay? And in our case, because we are considering a periodic boundary conditions, then those waves will appear again from the other side once they go over the boundary. Okay. So this is what we are going to see right now. So let's run the first cell. Okay, it may activate some package inside, which has some useful packages installed. If this does not work for you, simply comment this part and install the packages that you need. This works better if you have the full folder. Okay, and here we are defining some initial data, which is this exponential function. And this is not a numerical solution, this is just an illustration of what's going on. This is a nice animation that we have made. Okay. where we take this solution and we plot it. So in this case, this is phi. This is our the real solution for some function phi that we have defined, right? And as I said, it splits in two. These are the u and the v values. Okay, remember that u is the spatial derivative of phi and v is the time derivative of u of phi, right? So these are the two variables that we will evolve, and these are u plus and u minus, okay, which are a linear combination of these two. So what we will do is solve this system here, the diagonal system. Actually, we will solve this system here using this to define our initial data. And from this, we can later on find the value of phi. Okay. In general, you will not diagonalize the system that you have when you have a complex problem. This is a very easy problem where you can diagonalize it, but we work with this version here, with this u and v. And when you have a more complex problem, you will always work with this part. Okay. So this is what we want to do. Okay. So the first step that we are going to take, right, is to discretize in space. So we will take certain interval, in this case of length 1, and some number of points. We will choose 200 in this case. We'll define a delta x, a final time of integration. This will be the delta time, how much the time integration step that we will do in the Runge-Kutta, which in this case will be 1 times delta x. Here, in this vector, we will store the u values, the u and v values, right? So this is a matrix of dimensions n and 2. The first component will be u and the second component will be v. And here we define actually our grid, the grid coordinates. Well, and here we will define the finite difference schemes. Okay, so we will use here, we define the second order operator, right? It creates a little matrix, and here we also define the fourth order operator. And we are using some weird functions that you can see here, which are banded matrix, three diagonal spars, drop zero, stuff like that. This is not what you will be using in general when you want to actually solve a problem. When you solve a problem, you usually just simply define in each point, okay, I want to calculate the derivative of the y index. Okay, I will take 3 points to the left, 2 points to the left, whatever we need, we take the points and we do the operation in the cell. But this is the same as just having a matrix and multiplying by the whole vector of u, right, of the whole discretization of our function u and v in this case. And this is what we are doing here, just to illustrate, to create those matrices, which is actually what you are doing mathematically when you solve the problem. And because these matrices have lots of zeros, we do not want to store all the zeros, because we will just fill the memory of the computer with a lot of useless information. And this is why we use these functions that make spatial matrices, which are, for example, tridiagonal or banded with certain bands, right? And that do not store the zeros. The function already assumes that where it's not defined, it's a zero. Okay, and this is what we see here, right? This is, for example, the matrix. If the spatial discretization, the second order periodic approximation, if the matrix was 8 by 8, so if we had 8 spatial points, and this is the matrix for the fourth order. Okay, so we have two bands here, and so this will be a better order of derivative. Okay, and in this part here, what we are doing is simply defining the problem that we want to solve, right? We are taking V, for example, we multiply it by the D matrix, which will be the derivative, and we store it in du, right? And this h here is 1 over delta x, and this 0 here is because of certain arguments that this mul function requires. Okay, so the f will take as parameters r, which are the u and v, dr, which will be the derivative, which will be stored, right? P, certain parameters, which will be the spatial declassification delta x, and the matrix for the finite differences, and the time t, which will not do anything in this problem. Okay, so let me comment this here right now. Okay, and as initial data, we will put this solution here in particular. Okay, we'll put a u that goes up like a bump here, where we are using a high order polynomial to define it. This is where we are defining some p, which in this case will be maybe it's 8, for example. This is what we are doing here. We define some limits and points, and we define some u and some v. And v will be exactly the opposite of u. Why do we do this? Because we are actually trying to see this solution here. Recall that we have actually two waves, one which is u plus and one that is u minus. And here you see that u plus will be 0 and u minus will be 2 times u. So only u minus will move and u plus will be 0 all the time. So we will only have one wave moving in one direction. So we do not get confused with the waves interacting with each other. But you can change this to be anything you want, the u and v here, and evolve, and you will get some other animations, some other waves. Okay. Okay. So right now, let me check something here that this is okay. So any doubts up to this point? What we are doing in this particular cell is to define the operators, the matrices, right? Before we define the functions that create them. Now here we're saying, okay, create the operator, but with endpoints here, and then we define the parameters for the evolution, and we define the two problems, right? And this is the part that we will integrate using the Runge-Kutta scheme, right? And here we will put t and t. This is a modified version that I have, so you may not see this. And this macro here at time is something that we have included just to see how much Julia takes to run each of the cells. It may vary depending on how many things you have running in the computer. So for example, if you are doing a Zoom meeting, maybe it will not go as fast as other cases. But this is something for anyone who is interested in optimization. There are macros, and there are better macros to see in Julia how fast things are running. Okay. So here we will solve once, right? For the solution for the problem of second order, and in this case we will solve again for the fourth order. Again, this is second order in space, fourth order in space, and we also have a time discretization, which is fourth order in both cases because we are using Runge-Kutta. Okay. And now we want to plot the solution. Okay. And this is what we get when we use a second order derivative. Okay. This is the solution after 1 after t equals 1, 2, 3, and 4. Okay. Remember that we are having a solution. The length of the integration region is 1, and we are, in theory, moving with waves which have a speed of propagation of 1 also, right? This is what we are seeing here. There's a 1 here multiplying. This is the propagation speed in the x plus t, x minus t. So we would expect that if we increase time by 1, we will actually get the same solution again. The same solution in the same point. Again, if we evolve by 2, by 3, by 4, we will always get the same solution. We have a wave that moves, and then after one time step, after t equals 1, we go back to the same place. But we are seeing that our numerical approximation is not doing that. Okay, and I want to ask you, because we have seen this in the theoretical part, why this happens? Why is it that we are not getting back to the same point, but also that we are having all these weird oscillations in the end? Okay. Does anyone understand what's going on in this case? Because it is a good point to try to see if we get what the dispersion relations is and what the problem with these methods are, and how we can solve these problems. So in the chat you may put, this is because the x, y, z, whatever it is, or you can say, actually no, I don't know why this is going on. For the regions of stability, no, this is not actually related to the region stability of the method. The region of stability will have to do with the eigenvalues of the operator and the integration. But here we are, the eigenvalues are all imaginary, and we are using Runge-Kutta, so we are well inside the region of stability. Okay. Was the initial condition defined with some compact support? Yes, it was defined with some compact support in this case. Yeah, this is 0 and then goes up and then goes down. Maybe because of the discontinuity. Okay, the discontinuity there, there is no discontinuity in the boundary. There's maybe a discontinuity here in the derivative. In the 8th derivative there is some discontinuity, which is actually contributing a bit. But we could also have a solution here that's perfectly smooth, and we also would have this problem. Okay. So what's going on here is an issue with the dispersion relationship. Okay, so let us go a bit back and try to solve a different problem where we have some sign here. Okay, so in this case, some cosine. Let's talk about this problem. We will use a different initial data where we have a cosine defined on this region, right? So this will be the equation that we want to solve right now. Not this bump, but this cosine here. Okay. And we will do it again. Okay. We'll use a small delta t. Let me check if this helps here. Okay. 0.01 times delta t adaptive equals false. Let's see if this is working here. Okay. So this is the same plot I had before. Remember the one that I had the bump and suddenly I had all these weird waves that are going on. But in this case, what we have is this cosine wave that we started with, and we let it run, and then we go to t equals 1, t equals 2, t equals 3, t equals 4. And what we are seeing here is that the wave is not being really deformed, but what's going on is that it's not getting back to the exact point. It's like it's moving at a different speed. It's not moving at speed 1, it's moving at speed slightly less than 1. Okay, it's just going a bit late, right? So can you follow me up to that point there? If we do that again with the fourth order derivative, there is not that much issue. It seems to go back to the same point, although there is a little bit of difference, right? In this case, the second order, which is a very crude approximation, we see that there is a very high difference in the speed of propagation. So that's what's going on. We had our initial wave, right, which was a bump, and we can think about it as a Fourier series. So we can discretize we can express our initial solution, the bump, as a sum of cosines and sines, right, as a Fourier transform. And what we see is that each component of the Fourier transform is moving at a different speed. So initially we had a combination of sines and cosines that all cancel out to make this perfect bump. And then we make them evolve, and each one moves at a slightly different speed. So the higher frequency ones are moving much slower than the lower frequency ones. And suddenly we will have an issue because that bump starts to come apart, right? And this is what we were seeing before, okay? This is the issue that we were having, right? If we take a higher order operator, then we will not have we will reduce that problem, but it will always be there, okay? So let's go back to the problem that we had right here. Let's evolve a little bit. Okay, I did some better time integration so that you believe me that does not have to do with the Runge-Kutta, right? And here, for example, we see the fourth order derivative, and we see that this problem is still there, but it's not as bad. Okay, it's still there. There is some issue here with a weird wave that's going on there, and therefore we can see that if we go up to higher and higher order derivatives, this will be better. Okay, this is what we were talking about in this note here about the dispersion relationship. Okay, so I want to go over it a bit. Okay, just to understand what's going on, right? So we were can you see me here? Can you see this the nodes in this case? Okay. So we have our operator, which in this case will be this one here. Okay. This is the operator that we are using, the second order operator. This is this matrix here, which takes one point after we want to find the derivative of point y. We take y plus 1 and y minus 1. This is what we are doing in this time point, and then we are dividing by 1 over delta x, And when we take the Taylor expansion, we see that this gives us the derivative at that point, plus some terms that are second order in delta x. This is what why we are doing that, okay? So now let's try to, okay, let's try to continue here. What we are trying to approximate is this operator here. We are trying to approximate the operator of taking a derivative, right? This is the operator that we are trying to approximate, right? This is what the D is replacing. And this operator, taking the derivative, has certain eigenvalues, right? We are talking about here in the periodic case. So the eigenvalue of the problem will be exponentials, which are periodic, right? So we will have these eigenvectors with these eigenvalues. So if you take a function of this kind, we will get the same function again, multiplied by some eigenvalue, which is purely imaginary, right? So in our case, what we are doing is taking this operator here instead of this derivative, and we want to see what happens with those eigenvalues, the actual eigenvalue of the operator, the derivative operator, and see what's going on. And if we take the eigenvalues of the operator here, in this case, for example, we are taking the center, and we do, okay, what does it mean to take the discretization and do some and apply this matrix? We actually get this equation here. Okay, you can revise the notes to see what to see them, but we actually get this operator, right? This eigenvalue here, which is different from this one here. So we have this function a to the y to p kn xl, right? This is the function, which is the eigenfunction, the eigenvector of the operation derivative, and it's also some of them are also eigenvectors of our operator, the d0 operator, which is the second order operator, but the eigenvalues of the operator are this one here. There are signs, not this one here. Okay, this is what's going on here. This is sign and delta x. If we are using a very small delta x, or we are choosing a very small wave number, this kn here, which will tell us the frequency, the smaller it is, the lower the frequency, then this sign will be very close to 2 pi delta x. So 2 pi k delta x, so this will cancel out and we will get this relationship that we have here. Okay, are you following me up to that point with the eigenvectors and the eigenvalues? Yes, okay. So what's going on here is that this function here, the eigenvalues here, have this relationship with the wave number, the k value. No? So here we will have the eigenvalue here, and here we will have the wave number. And what we expect is this relationship here, 2pk. So we expect some straight line here. But what we get is that for small and small, for wave numbers that are very negative or very positive, we start to deviate from that line. And that if we take a higher order operator, then we get closer and closer to that straight line. But sooner or later, some high frequency mode will appear. All high frequency modes will always have some weird velocity that we do not want. Some different eigenvalue, right? So when you actually try to solve the problem, the derivative of t, the time derivative of u equals derivative, spatial derivative of u times some velocity a, which in this case in our problem is being a. You actually here you are putting the derivative operator, the d. Okay. Let me erase this part here. Okay. So here in this part, you are taking the derivative operator. Let me, okay. Here, and here you are replacing by the d operator that you are using. This goes, this is applied to the v, which is the spatial discretization that we have, and then you get this equation here. Okay. Okay, there are some notation here, but suddenly this problem becomes this problem. The time derivative of an eigenfunction will be a times this factor here times the eigenfunction. Okay, and when you solve this, this will be this is a constant, so this will always be some exponential. Right, this is the solution that we are having. When we solve this, let me move the chat a bit out of the way. When we actually solve this, we get that the wave here is moving this way. The eigenvector, when we try to do this, we see that the eigenvector will be e to the y2 pkn, and this is the exact solution. We will have a times t times these weird terms with the sign plus x. So what we actually want is a times t plus x, but we get this a times sine times t plus x. This is what we are actually getting. So what we see is that high frequency modes will move at a different speed. Not only that, they can even move at negative speed. So you have a solution that is supposed to be going to the left, and suddenly there's a high frequency mode that's going the other way. And this can be very dangerous because sometimes there are effects, for example, at the boundary of the problem that create high frequency modes that will start propagating inside the problem even when they should be going outside. In our problem, in this particular case that we are solving, right, and let's go back to the notebook. We do not have any boundary issues because we don't have any boundary. We don't have any real boundary, right? This is periodic. So this is the same as having the bump and then another bump and then another bump and infinite bump. So we are just seeing a region and it's the same as seeing infinite regions all at the same time. But the problem that we have is that our solution has some Fourier decomposition, and each wave of the Fourier decomposition is moving at a different speed. And we want them all to move at the same speed, which we will actually never really be able to do. There will always be a slight error, and that's why we need a high order operator and take a small delta x, an appropriate delta x, just to verify that this is going on, right? So for this, for example, is what happens after you evolve up to t equals 10. You see that the second order operator completely broke down. All the waves are all over the place, right? Maybe if we waited some very, very long time, they all come back together and they form again the initial data, but it's not going to happen anytime soon. And this is the solution at fourth order, okay? So, could you follow what's going on here in the problem then, in this case? Okay, so, perfect. So now we can talk about the conversion rate of these problems, right? So in this case, we are also going to calculate the Q as we did before. The difference is that before we were talking about the time integration. Right now we are talking about the spatial discretization. So what we are going to modify is not delta t, is delta x. And see, okay, I have this solution here, which has these weird waves, okay, whatever it is. If I had taken, instead of that particular delta x, a smaller delta x, how much better would the solution have been? No? And we expect it to go with delta x squared. That's what we were expecting, and for the other approximation, we expect it to go with delta x to the fourth, okay? So this function here, this is what it's doing. It's taking the u, some component that we are taking, maybe the u or the v, depending on this index y. We can put it in 1 or 2, right? And it takes 4 solutions, which certain delta x, then the delta x over 2, and then the delta x over 4, right? And we are doing again the whole solution minus the whole solution, right? And we are taking the L2 norm here to see the conversion rate, because we actually have to calculate this conversion rate using a specific norm, and in this case is the L2 norm, right? Other methods of solving, maybe we have certain conversion rates over different norms. In this case is the L2 norm that we need to use, okay? So here I am going to solve. I am going to choose a very small delta t, just so that I am only seeing error in the spatial discretization and not much in the time discretization with the unjecuta, right? That's why I'm also using adaptive false. And I am choosing, in this case, 160 points. Then I am going to choose 2 times that amount of points, and then again 2 times that amount of points, right? So let me try to fix it here, because I think I ran a cell twice and that will make it not work correctly. Let's wait for it to run. I don't know why it's going slow. Maybe it's because of the small delta t, but it should finish soon enough, right? What we're going to do is then calculate the q value at just after doing 1 delta t, and then calculate the q value again, but for several values of t, right? So in each time we see how the solution is going, how the solution is converging, to see if that fourth order approximation that we have, for example, in spatial dimension, is preserved when we continue to evolve in time, because maybe we're evolving in time and we are introducing some weird error, some weird interaction, and suddenly we are not having that same fourth order conversions, right? So this is something that maybe we are worrying about. Thank you. Let me check here. Yeah, that's what's going on. Here, okay, this should be a bit easier. Yeah, what happened here is that I ran some cells in different orders, so I multiplied by n again and again and again, so I was solving a different problem that I should have been doing. Okay, some 30 seconds more and it will finish running. In the meantime, I okay after this finish running, I want to just discuss a bit what the Kreis-Oligger dissipation operators are, because if you understand the problem that we were having about the waves moving at different speeds, then you will also understand what those operators are. Okay. So in this case, that we see that the Q that we have calculated is 15.5, so very close to 16. So we are in fourth order in space, and even when we evolve in time, that discretization is actually still pretty much there. It's going down here, but see the y-axis is still very close to 15.4, 15.5, right? Um, I think this is correctly done. Let me later on check, because maybe sometimes you make a mistake and this n should have been an n minus 1 to get the correct value, but I think this is correct in this case. Okay. And finally, we have this little section where we will add some noise here. So we'll make two solutions, two functions. One is the one where we had the peak, and we are trying to make it move. And then we will do the peak again, but we will add some high frequency modulation, where instead of doing this, the function will do tac 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 tac, see, go up and down, following that form, and see what's happening with that particular wave, right? So this is what we are doing here. We are creating two solutions, one with noise, the other one without noise, and here we are doing the animation. And you see that one is the smooth solution, that's going one way, right? It's moving pretty okay. There is some weird waves that are forming in the tail here if you look carefully, right? Maybe I can do some zoom here, and you see that there is this little issue with propagation speed, but the other one is moving to the left instead of moving to the right. Okay, so we see that this high frequency mode is not only moving with the wrong propagation speed, it's moving the other way entirely. Okay, so this may be this may be a problem. Okay, so if you have a high frequency wave, and with high frequency I mean with respect of the spatial discretization that you are using, right? Because maybe something that's high frequency in your discretization, where in each point it changes a lot from positive to negative, in another discretization it's much smoother and you don't have that problem, right? So in this case it's moving the other way, right? That's what's going on here in these nodes when we are talking about the Kreis-Oligger operators, right? The dissipation operators. Okay. What we are doing here with the Kreis-Oligger is think, okay, maybe I cannot avoid having these high frequency modes that are moving all around my solution and breaking stuff. But what I can do is try to change those eigenvalues here, which are purely imaginary, which means that these high frequency modes will not disappear, they will just move, and give it a small negative real part. So maybe I can change the operator G, so that this here, for high frequencies, is this plus some term that's telling it to decay. So we have our initial solution right here, and we have all these modes that are moving at different speed, but the modes that are high frequency, that's moving at completely different speed from the one we want, are actually going down. They are trying to disappear. They are actually being dissipated, right? So we will lose a bit of the solution, but at least we'll not have all this noise that will be messing up what's going on. And this is what the Kreis-Oligger dissipation operators do, right? So they do almost nothing when you are very close to a small wave number, but otherwise they have this weird dissipation relationship, and when you use them, suddenly this will be our operator. For example, in this case will be d0 plus the O20, right? And the eigenvalues will now have this written somewhere around here. Okay. The eigenvalues here, I cannot find it exactly in the notes, but it's written. We have this real part that's decaying. So when we apply some Kreis-Oligger operation, which I think there is an exercise about applying them, what you will see is that these modes, these little waves that are forming here, which are high frequency, suddenly start going down, and we get something much closer to what we expected. Okay. So this is the overview that I wanted to do about the wave equation notebook. I hope it was clear. I hope it helped understand some things about the dispersion relations and stuff like that, and what the problems are and how they are solved. Does anyone have any doubts about this notebook, or want to study a particular case? Maybe we can put some waves here and try to see what's going on. I want you to at least understand what's going on with the propagation speeds of the waves. So if someone could write in the chat or talk on the microphone. Okay, I see. I see there are no questions. I think it will be good to see. Okay. Do you want to see something now in particular, Felipe, or do you want to play with it a bit? Okay. Perfect. So, for example, I recommend that you go here and try to put some solution that's more like a cosine or something like that. Put a sign. I don't understand if the dispersion is caused by the different speeds and by the superposition of the noise. So the operator will you will have your solution, right? Which is something like this, right? And this you can actually decompose it as some sine wave like this, some other one that goes like this, right? Some other one that's high frequency, right? You make a linear combination of all of this, and you get this bump here that you wanted to do, right? So also of f of x will be some sum of sines of k times x times some coefficients c sub k, right? Or cosines here also, right? This will be our solution. We can do some Fourier transformation, and we will get this, okay? So in this case it's sines because we are using here there will be also a 2p factor here, and we are using here the interval of integration is from 0 to 1, right? So in 0 and in 1 this has to be 0, so we need here to have a sign so that it's 0 in these two boundaries, right? And what's going on is that each one of these parts is an eigenfunction of the final difference operator. So each one will try to move at a different speed when we actually try to do the numerical integration. When you actually when you apply the differential operator and then you do the ejecuta, each one will have their own speed, which has to do with this value here, and that's the dispersion, right? The dispersion is the fact that each eigenvector has a different propagation speed, right? What I was talking about with regards of the noise, this is a problem that we have just by being the exact solution. When I was talking about the noise, well, I was just pointing out that in other problems, you can have other factors that create some noise in the solution, some numerical artifacts. For example, in this case, we are having some boundary conditions that are periodic, so we don't have any boundary issues. But maybe you want to do something where you know what's happening at the boundary and you want to impose it somehow. You want to say, no, in the boundary, the solution has to move this particular way that I want to. And when you do that, suddenly you start having issues because this you want to approximate the derivative, for example, at the end, but you do not have points outside of the grid to calculate the derivative. So you have to start taking lower order derivatives. You have to mess the last rows and the first rows of the matrix of the difference operator matrix. And maybe when you do that, you introduce some numerical noise, right? When you are trying to impose a particular boundary condition, and that noise may be a high frequency noise. So maybe you're seeing some noise and you think, okay, I have some noise, but the noise should have a propagation speed that goes outside of my region, so I don't see it anymore. But because it's high frequency, suddenly it starts entering your solution and starts messing up. We are not seeing that here. What I was doing in the last one, so it was just in the last part, was just imagining that I created some high frequency node here, like there was some high frequency solution that's going on there. Maybe it's because I wanted to evolve it and that's what I got. Maybe it's maybe it's because there was some issue at the boundary, whatever it is. What I wanted to show you is that those propagation speeds will not necessarily stay close to the real propagation speed, and not only that, but they can also go completely the other way. So that can be very, very annoying. Maybe you are working in general relativity and you have some waves and you say, okay, I have some noise here, but at least I know that the noise will go lower than the speed of light. No, it's numerical noise. It can go whatever speed it needs to go according to the operator, and maybe it's going faster than light in your problem, and suddenly you are evolving a black hole, and suddenly you have some weird wave that's going around that you don't know why it's there, and it actually is coming from this some weird effect in some part of your code that's propagating this way. That's why you use these Kreisfördiger operators to take those high frequency waves that are usually noise, right? Because usually when you have your solution, you are trying to capture all of your solution, so you will not try to evolve something that oscillates faster than your own grid. So you take all those high frequency modes and you try to dampen them, to give them some coefficient that makes them decay exponentially. So is that clearer, Virginia? Okay, perfect. So you see here in this case, for example, you see the wave package is moving, but there are also like smaller parts in the wave package that are also moving in their own velocity, because this also has some weird Fourier transform that's doing this effect. Okay, any other questions regarding this notebook? Does the method of flat work well with weak non-linearity? So it depends on the problem, but the problem with when you have non-linear equations is that you will eventually develop a shock in the solution, right? So maybe if you have some dissipation, it will work okay. But if you do not have a dissipation, so maybe if you have a problem like this here, right? So here we were solving ut equals ux, right? If suddenly here I multiply by u, right, and try to solve the solution, this one will develop a shock. So you will have your initial wave, and suddenly you will have a discontinuity, and this will be general. But maybe here you have some component that has to do with a second derivative in x in u, and this one here, this term will add some dissipation, and suddenly that discontinuity will not be there anymore. It will be more smooth, and then you will not have that issue. So in general, if the problem is non-linear, maybe this is not the way to go. In the exercises, you will have that. There is an exercise where you have to take this problem and try to solve this equation here. And what you will see is that you start with something like this, right? And suddenly you get this. Right? Suddenly this wave is moving this way, and suddenly there is like this high discontinuity that appears, right? And that will be terrible for our method, because suddenly you are trying to do a Fourier transform or something that's discontinuous. And if you remember, that will give you the Gibbs phenomena. So if you have this, for example, and you try to do the Fourier transform, here you will actually get, if you go to certain order, you will actually get high oscillation here, and high oscillation here, and high oscillation here. Sorry, will actually be more like this. And here you will get very high modes that you will not be able to avoid even if you go with a very small delta x that will always appear there, and this will completely mess up your solution and will become unstable, and it will crash after some time. So if you have some dissipation, maybe, yeah, because then this will not be sharp. But if it's like this, completely non-linear, then shocks will appear. And this is something general about non-linear systems. So if you have ut equals fu, and we drag this over dx, if this f is non-linear, then you will form a shock eventually. Or some rarefaction waves in some case, but the solutions will develop shocks. In our case, we are taking here linear, so there are no issues, and if you have some dissipation, then there are also no issues. We will actually later on see in the course how to deal with these equations that actually have discontinuities, which is a method that goes another way of solving the problem, but it ends up with a very similar solution with final difference when you actually take a closer look at it. Any other questions? About this part? Otherwise, maybe we do a little break, and if you want, later on in the last part, we can go back again to with the topology homework to finish stuff we talked about yesterday. I don't know if you still have any doubts about it or this notebook. Okay, so if there are no questions right now, I will pause a bit and we'll be back in, I don't know, 10-15 minutes. Leco, ¿te parece? Oh, okay, so 12:25. Okay. Okay.